So let's get right into it. Here we have the x-axis and the y-axis and a few points here. Now each of these points is going to have an x-coordinate and a y-coordinate. The task of our machine is to learn this data, and what that means is that the machine has to come up with a line that best fits the data. Now this machine is nothing but a computer program, and basically we have to write a computer program that is able to best learn this data, which is basically come up with a line that best fits the data. Now that line should ideally look something like this, because this line goes through most of the data. And to come up with this line, the machine has to come up with nothing but W and B, because W and B completely define this line. And just to revise, W is nothing but the ratio of this height by this width, and B is nothing but this height. So the machine has to come up with these two values, W and B, to basically come up with this line which best fits the data. Now to begin with, the machine has no idea what these W and B are going to be. So it is going to assign random values to W and B and see whether they are good enough or not. And with those random values of W and B, the line that the machine would come up with is going to look like that, because these are random values and these would not fit the data. So the machine has to find the error associated with this line so that it can improve its W and B values such that it eventually concludes at a W and B which best fits the data. So it has to start with calculating the error associated with this line. And the way it goes about it is as follows. So for every point in this data space, there's going to be an x-coordinate and a y-coordinate, and we are going to calculate the error associated. So for example, for this point, this is the x-coordinate and this is the y-coordinate. But the machine has gone and predicted this as the y-coordinate because that is what falls on the line for that x-coordinate. So the error associated with this point is going to be the distance between the actual y, which is here, and the predicted y, which is here. So this is the total error associated with this data point. Now with this data point, similarly, this is the x-coordinate and the actual y-coordinate is somewhere here, but the machine has gone and predicted this as the corresponding y-coordinate due to this line for that data point. So instead of predicting this, it has gone and predicted somewhere here. So the difference between the actual y and the predicted y is going to be somewhere here, this much. And that is the error associated with this data point. Now similarly, if we calculate the error with all of these data points and sum it up, we're going to get the total error associated with the entire data set. Now you can imagine that this data set might have millions of points, and we don't want to deal with an error which is going to be high, so high that it is going to be difficult for the computer to represent it as an integer or a floating point number in its 16-bit or 32-bit capacity. So instead of finding the total error, what we find is the average error for each of these points. So what we actually do is sum up all of these errors and then divide it by the total number of points. So we get average error for each point. So this average error for each point is called nothing but the cost. So the cost associated with this line is the average error associated with every data point. And the task of the machine is to reduce this cost such that it comes up with the best possible line, which has the lowest cost. Now, just for visualization, you can imagine that the real solution is going to be somewhere there, that line. But if the machine predicts something which is so off, the cost is going to be very high. But if the machine predicted something which is close enough, like let's say here, or on the other side, let's say here, the cost is going to be a little higher than the actual cost, but not as high as this. So you can imagine that this is the lowest cost, and on either side of the actual line is going to be a slightly higher cost. So you can imagine that this is the best line, and for this line the cost is slightly higher, and for this line also the cost is slightly higher. So if you were to kind of visualize this cost, it would have a minimum value somewhere, right? This is corresponding to the actual real solution, and the cost goes up on both sides of that line. So to help you imagine better, we are going to break this figure down into the basic components of the line. So what this point really means is that the cost is lowest here, and this is corresponding to the best line. In other words, this is corresponding to the best W and B values. On the other hand, a point which is here is corresponding to a high cost, and it's corresponding to bad W and B values. So these W and B values are actually parallelly calculated by the algorithm or by the machine. And if you want to imagine this better, think of this bowl-shaped curve where instead of having just a two-dimensional curve like that, I'm having a bowl where this axis represents W and this axis represents B. And the algorithm has to parallelly reduce the cost by finding the best W and best B. So the cost goes up higher on all sides of this bowl-shaped curve and is lowest at the bottommost tip of this curve, which corresponds to the best value of W somewhere here and the best value of B somewhere there. So that is the task of our algorithm. So let's say the algorithm comes up with the best value for W, which is going to be here somewhere, but it still has to come up with the best value of B. So that best value of B can lie anywhere on that line which is passing through this particular W. So for that W, we actually have all possible values of B. So the task for the machine is to find both the best value of W and the best value of B. Now the rest of it will be covered in the next video.